Okay, so yeah, as you can see, there are a lot of technical issues. And the same for our plasma device. Well, we're still trying to figure out how to optimize all these parameters from the front stage, from what Michalis and Ija, they are doing. And from our aspect, from University Antwerp, University Ghent, and also Pisa, and also other museums, we are trying to see how it really works about the soot removal from different kind of substrate. Yes, and I will be representing our university and also Marta, my colleague. We will discuss about the first results on undyed silk, and let's see how it's removed. The soot are removed. So before just starting my presentation, I would like to just leave a sentence here why we're trying to remove soot from all different type of contaminants. So soot, they were quite actually reacted to atomic oxygen as we tried out all different type of contaminant, and it works pretty well. So that's how we choose these substance as our target. So the outline of my talk today will be divided into three sections. The first, of course, we start with the preparation of the mock-ups. And the second, we dive into this AO cleaning performance, how the soot were removed. From at our institute, we will focus on undyed silk. And then at the end, I will end up with the benchmarking, which Marta, she's doing. So, as you can imagine, to produce soot in a closed environment is not an easy task. And we've been trying a lot of different reproduction methods. There are in total 5 methods. We summarized the first 3 methods, including shaking, rolling, and spraying. And these 3 methods, they were so-called indirect cold applications because we applied the soot in a form of soot dispersion in ethanol. And the soot we are using here is supplied by Kremer. It has a higher crystallinity compared to the real fire soot. And all these 3 methods, they were applied at the room temperature. The other 2 methods, the candle burning and the soot drum, that I'm gonna discuss more here. Both of them, they were hot application, which means they are basically the combustion of hydrocarbons. And there's a problem for candle burning because, as you know, the heat of the flame is quite hot, which can easily burn our sample. So we can't just use simply candle burning. So we built up a device, a soot drum. Here you see on the right side. The sample are in place on the rotating plates, and the plates is put inside the drum. And with the combustion of shell so D40 in the bottom of the drum, we can get a homogeneous soot deposition. And I will go more into detail about the soot drum we have here. It's a whole process, including the burning in the drum and also preparation of other like motors for the rotating plates. Yeah, and also, it's I would say it's a kind of dirty work. We get soot every time together with the sample. And the important thing is here, I can show you how it works. So the samples, as I mentioned, they were attached on the rotating plates, and they are rotating by controlled by the motor. You can see from the hole on the top of the drum. And how's the result? If it's good, is it homogeneous? Yeah, So here are all the samples that we suited. They include all different type of materials that provided from all of our partners. So about the silk mockups, so it looks nice. At the end, we are satisfied with the suiting process. So here we use a pongee silk. It's undyed, and you can see clearly how it looks like before and after the suit reproduction. So I would say the whole suiting process is quite important to make a homogeneous suit distribution on the sample. So then after the cleaning process, we can evaluate the performance, whether with the AO or other cleaning method. So as you see here, this is the real plasma jet. Okay, anyways. Yes, so basically we need to put our sample on the stage, and it's exposed to atomic oxygen at a certain distance. As already Michali he explained, it's important to know where it's placed under the atomic oxygen, and also how long it's treated. Here I would like just to show you the heating effect that's together with the atomic oxygen generation. So here, it's the power, the value of power is a little bit small, but here I'm trying to increase the power, and here you can see the heating effect. The area expanded, and also the temperature in the center is hotter. So it's important to see how it can go, where are the range of power and the exposure time. So we started with a single spot without moving. So as you can see, there's a huge difference between 4 watt and 8 watt. And also by increasing the exposure time from 1 minute to 10 minutes, the cleaning area is enlarged. And also, it's more clear to see at a higher power, at 8 watts, you can have a certain damage in the center, especially. And this is in the case of organic silk object. And we also have a different limitation for this heating effect for different substrates. So, together with the VP1, we need to figure out how this heating effect, where's the limitation of the power, and also how it's correlated with the atomic oxygen distribution. And this will be done with the TALIF technique. So in practice, we can't just clean an arced object with a single spot every time. So in our lab, we use a moving stage on the X and Y axis. We place the atomic oxygen, the plasma jet fixed, and our samples are placed on this moving stage. And here's how it's cleaned, with this moving path. It's a program script that we need to optimize also for the cleaning. So here's the optimizing process we did for a larger cleaning area. So as you remember in the previous slides, so the distribution of atomic oxygen and also heat is different from the center to the outer boundary. So here we optimize the speed and the gap between each line we put here in order to clean a 2 by 2 centimeter square of the suited silk. So at the end, we managed to clean a larger area, which is homogeneously cleaned. So yeah, more about the optimization of cleaning parameters. So the first one, as we mentioned many times, is the power. As you see, we can clearly see a difference from lower power, 4 watts, to 8 watts. You have a better cleaning effect. From slightly cleaned to halfly cleaned, or let's say completely cleaned, to, of course, the end we want the super, there's no any residues anymore. And here we can conclude that 6 watts seems suitable for most of the organic substrate. We've been tested paper, textile, and some of the plastics at the 4 millimeter distance. And 6 watts seems quite safe for organic substrate, and especially when we try to move faster. So the heat can be spread all over the sample, but not just focusing on one single spot. And of course, for inorganic materials, we could have even higher power. So it depends which substrate you are dealing with. So we would like to confirm if there's soot residues on our sample, and also we need to know if there's a certain damage after cleaning. Yeah, the same experiment was about the exposure time. We increased the exposure time from 8 minutes to longer, within 1 hour. Just to control it will not take so long. And the same experiment was done also on unsoiled sample, on pristine samples, just to validate the results, especially focusing on the damaging to the substrate. And the main focus of our study is the evaluation of cleaning results. So how to evaluate in a systematic way, because in our project we have so many different type of substrate, and also the morphology, the surface structure is kind of different, and also in the future we would like to move on to other type of contaminant. So it's important for us to first to know how to evaluate the methodology for evaluation. So our first step is to use optical microscope to have a visual analyze before and after cleaning, and also at a different power. With the image J, we could get a brightness value of this optical microscope image to see how the brightness changed. Because based on the soot contaminant, we can say the darkness or the brightness is determined by the amount of soot that remain on the sample. So visually, it's confirmed, with our eyes, and also we didn't see any damage to the silk thread at certain condition, the condition that we selected. And also we use the colorimetry to calculate the change in brightness in another way, apart from the image J brightness value. So instead of using the traditional change in delta E, we also decided to use the brightness again here, as we then the delta E take also into account the potential color change of the substrate. So we don't want to see now here for the substrate, but just to see how much soot were removed. So that's why here we selected the delta L. And also this delta L value or confirmed with the previous brightness change. And then, after the evaluation of the soot removal, we could move on to see the impact on the substrate. So here is a brief. It's quite a harsh condition here. Yeah, don't get scared. It's more than what we need for the cleaning of soot contaminants. But here, just to let you to see how it can be if there's a higher power or a longer exposure time. So the reason we could imagine for the damaging of this silk thread could be a co-effect of atomic oxygen, the reaction between the silk and atomic oxygen, and together with the heating effect. But this also is one of the tasks for VP5. So they will explain what are the changes in the silk polymer chain, and also from the volatile they could detect. About the characterization of these volatile. Here I would like to add it. For VP5, they could detect what are the volatile compounds that after the AO cleaning, they could try to find a way to absorb all these volatiles and then transfer to GCMS. And then, they could analyze what's happening there. And at the end, I will just represent Marta, my colleague. She's doing a benchmarking of the AO assessment through comparison with other cleaning methods. So, the same methodology also valid for the other cleaning methods. So regarding the evaluation method, a comprehensive protocol is currently under development. The goal is just to see, to incorporate the qualitative and quantitative methods to access and to assess and validate the AO cleaning performance. So here there are tons of different cleaning methods. Here we pre-selected the promising cleaning methods, including dry cleaning, solvent cleaning, gel cleaning, and laser cleaning. And is specifically selected for soot removal. And here you can see the results is pretty nice. We can see AO cleaning is promising against the other methods. And of course, there are also a lot of other parameters, including cleaning time, which are also important, and these will be further investigated by Marta. Here is just some examples how it looks like under microscope with the different cleaning methods, including micro vacuum, PU sponge, and microblasting. Also, solvent and gels are included. And more important here, we would like to compare the laser cleaning with AO cleaning, because both of them, they are contactless cleaning methods, and in some way it's more more important to compare these two techniques, and it will be done at University of Pisa. And the same evaluation method using colorimetry. As you can see at the bottom, the AO cleaning effect is more promising compared to the others. Also for the force spectra. And finally about the SEM examination. So with SEM we can evaluate if there's still soot residues left, and then we can tell if we need further cleaning, a longer treatment or not. And also the same for laser cleaning, we could see whether there's a certain damage to the silk fiber. So for just to conclude, from our first visual evaluation, the air cleaning seems to be quite efficient compared to the other traditional cleaning methods. But yeah, however, there's a certain damage at a very harsh condition. So that's why we need to optimize the cleaning parameters, including exposure time and the power. And at the end, we will also do aging, aging for all of our substrate after cleaning to see if there's a eventual longer-term effect of the substrate. No, that's all for my presentation. Yes, and you are welcome to talk with us, me and Marta, during the lunch break. Thank you very much.